So we move on and calculate for x from delta 1p plus delta 11 x1 is equal to 0. So delta 11 is equivalent to 4 over 3 ei times L cubed, which is supposed to be equal to, when this one here crosses the equal sign, it becomes a positive, so it becomes 5 over 8 q L power 4 divided by e I. So the ei and the ei cancel, then the L is also cancelled, remaining with only one L on this side. So our x1 would be equal to 15 over 32 q L. So having found our x1, we now move on and calculate for the moment, which is given by m1 x1 then plus m. So our next example is as follows. We have a structure that has got two rigid supports, and then here it has got an axial member. So as we said, the first thing, as always, we need to first find the basic structure. So from this one, what do you think would be the best way to come up with a basic structure? Yeah, the easiest way would be by because if I am to look at this support here, I have three reactions, isn't it? So if I'm to make a basic structure by creating my x's at this point, that means my process of calculation would be so complicated. The easiest one is by us dissecting through this member here. Since it is axial, it will only be having one force, that is the axial force x1 on that side, and then also on this side x1. So that would be the best way to deal with this. With that in mind, we go on with our process of calculation. First of all, let me first extract the basic structure and draw it on its own. So the basic structure would be of this format. We'll be having that, and then we've dissected it in the middle, and then this other half of it like that. So here we're having, okay, for the forces, let me make them to be coming inwards like that. It doesn't matter, any way you make it, you can do the calculations, but for this sake, let's use the forces which are showing a compression. And then here we have a hinge here. So these forces have a magnitude x1. So that is our basic structure. So after doing that, we said we have to come and draw the bending moment diagrams due to the original loading, and then the bending moment diagram due to the action of the unit force. So the bending moment diagram to the action of the original loading would be as follows. So I do have a structure of this nature with a hinge there. Then yeah, we don't have a force here on the original loading, so here we know that we can see that here it's being acted upon by a distributed load of magnitude 10 kilonewtons per meter. So therefore, for a distributed load, like we know it that it will be forming a curved shape, and then this beam here still resembles a cantilever beam, though here it has got this hinge, but then there is no force at all acting at this point, and then at the hinge you know that the moment is 0. So the maximum value of it would be this base with a value of what? With a value of a half q l squared. So our q is 10 and then our l is 6. Then 6 squared is 36. Divide by 2, that is 18. So this becomes a 180 kilonewtons per meter. Then, so this is what we are calling the MP. Then we come and draw the other drawing else, that is the M1 drawing. So the M1, under the action of the unit force, x1 is equal to a 1. So when it's being acted upon by x1 is equal to 1, like the beam is being pulled towards this side, then this side is being pulled towards the left. So therefore, it will be for the sake of pulling towards the right hand side, this side would be under tension, and then since it's a cantilever beam, the graph would be of this nature. This would be having a magnitude of 6. Then on this side it will be on this outer side, because this is a side that will be under tension, also of magnitude 6, like that. The 6 is got by force times distance. So having done that, next now we come and solve for it. We come and solve the equation, the delta 11 x1 plus delta 1p is supposed to be equal to 0. So our delta 11, we say that one there is got by multiplication of the M1 drawing. So it will be given by 1 over EI, then into we notice that these two shapes are the same. So therefore I just work with 1 and then I multiply by 2. So the area would be a half times the base, it will be a 6, then times the height is a 6. Then our center, because the center is from the same drawing, so it will be the center is somewhere here. Then this distance here from this point up to this point would be a 2 over 3 of this distance here, times 2 over 3 L, and then our L is a 6. Then there are 2 of them, so times a 2. So this would be equal to 144 divided by EI. Then we come and find the delta 1p. Delta 1p would be given by 1 over EI into, we already have this single shape here on this side. So its area is given by 1 over 3 times base which is a 6, then times our height, then times the base which is a 180, like that. Then now times the height at the center, so its center is somewhere here, a distance of 1 of L over 4 from the base. So I come and I draw the line up to this point on the triangle. So from the triangle I'll need to find this height here, So since like it is a 1-to-1 triangle, if I know like the ratio between the base of the triangle and then the height is a 1-to-1, that means even the ratio between this one and this one for the small triangle must also be the same, 1-to-1. So this one here would be 3 over 4 L. Therefore that means this height would also be 3 over 4 L. So I multiply this one times the 3 over 4 times L. Our L is 6. This would be equivalent to 1620 divided by EI. So having found that, I now come and I calculate for my x1. So the x1 we shall be having x1 times 144 divided by EI should be equivalent to Yes, so since this delta EP is a positive, so when it crosses the quotient it becomes negative 1620, then divide by I. When I work out this, I'll find that my x1 would be equal to 11.25 kilonewtons. So having found this, now next we come and draw our final bending moment diagram by superposing the moment on the M1 times x1 with that one of the MP. This gives us the final moment on the bending moment diagram, like that. So to do the superposition, we have now to multiply the x1 times the moments on the M1 diagram. So this should be negative 11.25 times the 6 which is here. I would be getting my answer as a negative. Let me use a different color. As a negative 67.5. Then even this side it should be a negative 67.5. So for this case, since it's a negative, that means that our actual bending moment diagram now would be having this look here. It would be something of this nature. Sorry, let me try it here. So instead of being on the outer side, it would turn to the inside part, that is with now a positive 67.5. Then even this side here would be positive 67.5. So this becomes the M1 x1 diagram. Now from that we have got to superpose this diagram here with this one here by adding the moments at the points of interest. So what do we do? If let's say this way we are drawing our final bending moment diagram, then here we've got hinges even here like that. So I know that the moment at the hinge is equal to a 0 for this one, is equal to a 0 for this, also here it's a 0, so here I have a 0. Then for the sake of this bottom part I have 180, here I have 67.5 but on opposite side, so I'll take 180 minus 67.5, then that one there would give me 112.5. Therefore at this point I would be having my moment as 112.5. Then I come and I construct my bending moment diagram like that. Then for the sake of this right hand side, I don't have any moment on the MP diagram, so the value is just as it is for the sake of as it is on the M1 times x1. So this becomes 67.5, and this is our final moment diagram. So thank you.